Good morning, everyone. We'll pick up from this slide here on temperature conversion. So I just want to talk briefly about converting between degree C and degree Fahrenheit and also into the Kelvin scale in case you haven't seen this. If you would need to do temperature conversions, we'll give you these equations. We won't expect that you memorize these equations other than maybe perhaps once we get to it, when we start to do a lot of Kelvin to degree C conversions. I'm not entirely sure we always give you that equation, but when we get there, that's such an easy equation. That'll be like chapter 10 when we start using that equation, maybe more frequently than here in chapter 1. But just to introduce the scales to us, we have them here where we just simply add 273.15 to our degree C temperature to go to Kelvin. Now that's our absolute zero scale, so you cannot have an object go below 0 Kelvin. So the Kelvin scale is the one that you would use if you don't want to have negative temperatures. And so then Fahrenheit, of course, versus degree C, just a simple conversion between the two. So we can go to Fahrenheit by taking the degree C temperature times 9/5 and then adding 32. And then just rearranging for degree C gives us the equation here. And so I just wanted to make sure that we can come up with an ordinary temperature in our scales in case we haven't seen these scales or thought about them recently. So if we want to calculate a temperature in degree C from Fahrenheit, we would just be using our equation here. So this is just going to be 5/9 times the quantity, the degree C temp, or the Fahrenheit temperature, and then minus 32. And so if we take 32 away from 77, multiply by 5/9, this is going to actually give us 25 degrees C. So when we think of, sometimes we think in degree C that room temperature is about 25 degrees C. It's actually kind of a warmer room. It's about 77 degrees in Fahrenheit. And if we want to calculate the temperature in Kelvin from here, then we're just taking our degree C temperature and then adding 273.15. That's going to give us 298 Kelvin. We'll talk about significant figures in a minute on why I would probably round this to 298, not 298.15. But 25 degrees C, we're just simply adding 273, going to 298 Kelvin. So kind of room temperature, or room temperature-ish, if you will, in Kelvin's about 298 Kelvin, 25 degrees C, 77 degrees Fahrenheit. One last thing to point out is when we compare our scales, I think we probably all know water boils at 100 degrees C, melts at 0 degrees C. So we have a 100 degree spread at standard pressure for the melting and freezing point of water. And if we go to Kelvin, we're just simply adding 273 to those measurements. So we're going from 273 to 373. So we have 100 Kelvin spread from 0 to 100 degrees C in Kelvin as well. So when we think of going up 1 degree C, if we go from 25 to 26, we're going 298 to 299. So our difference in temperature, this is something we'll use a lot actually in chapter 5, but our changes in temperature in Kelvin are exactly the same as our changes of temperature in degree C. So if you go up 5 degrees in degree C, it's the same as going up by 5 degrees in Kelvin. You're just going up in an absolute difference between two different numbers, and Kelvin is all. So 100 degrees C from melting to freezing, and degree C for water, same thing for the Kelvin scale. And of course, that's not true for the Fahrenheit scale. So the melting to the freezing point difference for Fahrenheit is almost double that. So it's 32 to 212. So a little bit of a different spread. So we don't use Fahrenheit too much in this class, but we use it more commonly, obviously, outside of class. So just wanted to point that out. And so I just thought we'd do a quick little example. I give you guys maybe a minute to think about this problem, maybe 2 minutes. Try to convert or determine how many nanometers are in 0.025 centimeters. You can try this on your own if you want. If you want to compare your result with your neighbor, feel free. And just try to do this from your memory of the conversion factor prefixes that we were talking about on Friday. see if we have any consensus. How many think it's A? Anybody think it's B? A couple B's. Anybody C or D? C or D might be if we flip our conversion factors around. Okay, so let's think about A versus B for a minute. So when we think about, or how I might make this conversion is I'm thinking maybe centimeters to meters, and I might be thinking meters to nanometers of doing this conversion in 2 steps. Something there's 100 centimeters in 1 meter. Then I'm thinking to go to nanometers. I'm either thinking how many nanometers are in 1 meter, or I'm thinking what's the size of 1 nanometer in meters. So I need to make the conversion one way or the other. So I'm going to think 1 meter should have a lot of the nanometer because the nanometer is really small. So 10 to the plus 9 nanometers. And then the difference between, I think, answers A and B is going to be just like simply maybe making a calculator error on how we're putting this into our calculator. So if we go 0.025, divide by 100, we just have to multiply by 10 to the 9 or 1e9, just something that gives us 10 to the 9. And I just like to hammer on every now and then I see the error being that students will enter 10e9 for 1e9. If you use the conversion in your calculator 10 times 10 to the 9, then that's probably why we got answer B. So the answer should be A here. And if you're getting B, I bet it's just a simple calculator issue. And so when we're putting this into the calculator, our 2 options are going to be 10 to the 9 or 1e9, but not 10e9. And so I so frequently have seen 10e9 that I like to point that out here. Okay, so that gives us the number of nanometers here. Also, we'll see a few more examples in dimensional analysis, but just kind of starting, with the problem, what is it that we want to find? What's the unit that we're given? How can we make our conversion so that we get towards that unit through converting those units? Okay, so let's get into kind of like the last topic that we haven't touched yet in the chapter, significant figures. So let's have a discussion of what is going on and what this topic is about, and get into some examples and what we want to take away from this topic. So all digits in a measured quantity, including the uncertain ones, are what we call the significant figures. And so this is going to get at when I see, something like 1.25 grams. When I see this as a number, then I'm assuming this is some ordinary lab measurement. So this is a measured quantity, or I'm imagining it's a measured quantity of some object and its determination of its mass, maybe with a balance. And then this last digit in the number, there's going to be some uncertainty here. And once you get into the lab, or if you've ever put anything on a balance, especially one that goes to 2 more decimal places, you've probably seen that last digit going up and down, probably pretty commonly. And that going up and down is the uncertainty in that last digit being really visible to you. If you're using a scale, like an actual physical scale, where you have some sort of like an object, and then you have 2 dashes, between the scale markings, and you're trying to interpolate how far in between the dash markings it is, that's something about your uncertainty. You can sort of argue and come up with, is that halfway across? Is it a third of the way across? Is it a quarter of the way across? Is it 0.3? Is it 0.4? You can see that you can have some significance that it's definitely not, like if we're imagining this marking is between 0 and 1, it's definitely not 0, definitely not 1. It's probably 0.3, 0.4, somewhere in that range, right? And we can argue and have some uncertainty if it should be 0.3 versus 0.4 in that type of scale. Same thing with a balance or something that has a number. Whoever made the balance, there's going to be some waffling in that last placeholder that we call this our uncertain digit. Now, it doesn't mean we don't know that digit, or doesn't mean that there's such little significance in that number that it could have been 1.22 or 1.27 or 1.29. We think it's 1.25 with a good probability. We just think there's some inherent uncertainty in that digit. In statistics language, we would say that there's at least 0.01 grams of uncertainty. There's at least plus or minus 1 unit in that quantity's placeholder of uncertainty. And if you take a stats class, you're going to learn how to propagate error. You're going to learn how to take that uncertainty and track it through a calculation. Here, we're going to try to come up with just a really rudimentary set of rules that we can apply so that we don't have to do the statistical analysis and apply any kind of fancy statistical analysis that you might learn in upper level stats classes. And so when we start rounding with these calculations involving these types of numbers that are involving measured quantities that are inexact quantities, we have to pay attention to where the significant figures are so that we can properly state the significance or the preciseness of a result. So if we do a multi-step calculation and then we look in our calculator and there's like 9 digits in the calculator, we want to know where should we round that value to with some reasonable expectation of precision. Where do we want to round that result to based on the quantities and their uncertainties in the problem? That's where significant figures and our rules that we're going to get into are going to relate to, is like how do we round off our values properly? And this comes up a lot in the lab. When we're actually doing careful lab work, we want to be as careful as we can to understand how many decimal places are significant or how many of the numbers are significant in our calculations, and then where we should round off to at the very end. And then sometimes I do a demonstration. I might put a video of this up, but there's a relatively straightforward thought. I thought maybe a thought today would be like, let's say you wanted to measure like your Apple Pencil and try to figure out how long the pencil is. Well, let's say you had a couple of different scales available, and let's say one of the scales was really bad. So we have scale 1 we can place the pencil onto, and scale 1 just has a marking at 0, a marking let's say at 5, and a marking at 10, and let's say that this is centimeters, just to throw a unit on here. And we can imagine taking our pencil and trying to figure out on our scale. Of course, you can't see where it is on the scale, but let's say our pencil's ending right about, am I doing that? Somehow I caused feedback. Okay, so let's say that the pencil goes all the way to this point here. And so we have our pencil to this point here, and I have this terrible scale that I'm using. Now, do we think that's 5 centimeters, or do we think it's 10? Or do we think it's some number that could be between 5 and 10? Probably looks, would you guys agree, about 9 centimeters on this scale? So I'm looking at this scale and I'm saying, okay, my pencil is probably about 9 centimeters. Is as good as I can do with this scale. I can do better than 5 or 10. I don't have to round to 5 or 10. I can interpolate between a scale. Now, what if I simply improved the type of scale I was using? Let's say I grabbed a better ruler that had markings every centimeter. So let's say I had a marking at 6, 7, 8, and then 9. This is maybe not drawn to perfect scale, but hopefully giving you a sense that if we had the scale markings showing us a marking between 8 and 9, I can now look and see, okay, this actually looks closer to 8.6 centimeters than it does 9 centimeters. Okay, so it's all about the scales that we use. The pencil itself has an actual length. Maybe we could look it up. Maybe we can use a much finer, we could even look up and use a better scale that has more graduated markings, and we can get another decimal place on here. So if we want to measure this ourselves, we're limited by what type of scales we have available to us, what type of rulers we have available. If we have a good ruler, we can determine this length very precisely. If we have a poor scale like the first one, we can determine it to a very low amount of precision. So if we want to know it's 9 versus 8.6 versus 8.65, the amount of precision we want to have, the number of like decimal places we want to know the length to, depends on the scale that we use. Now, the object always has some true value. So there is some actual length of this thing that if we had the most precise scale in the world, we could determine. The issue is we're never going to have that most precise scale. We have the scales available to us that are going to be limited to being, like 0, limited to like 1 sig fig or 2 sig figs or 3 sig figs or however many we can get off that scale. And so a bad scale, we get 1 sig fig. A better scale, we get 2 sig figs. Improve the scale further, maybe we can get a third, maybe we can get a fourth. But the object still has, like, one of the confusing parts about significant figures is the object has some true value, it has some like real length, but the question is how well can we characterize and know that with the scales that we're using. There's a few different other examples. There's another thought problem I like to use, which didn't used to be funny on counting crowds, but if you imagine the thought process of trying to count everybody in this room, if we close the doors and we very precisely got maybe a few different people to go through with like maybe counters so we can count everybody in the room. We do this a few times. I'm sure we could come up with a very precise head count of everybody in this room and be 100% certain of how many people are in this classroom. Now, if you turn this into like a theater, if you turn this into like a stadium, all of a sudden we're not going to be able to make that exact determination anymore. We're going to be estimating or approximating. So there's a difference between whether we can physically count that there's exactly 300 people in this room First, if I'm gonna like just look and say, oh, there's probably about 300 students here today. And so if we say there's exactly 300 people in the room and the door opens, 4 people walk in, how many people are in the room? 304. And I think you can very easily see the difference if I just say, and if we just approximate there's 300 people in the room, 300 people plus or minus, let's say, 25 people, how well could you approximate a crowd size just by looking? So I say there's about 300 people in the room, probably plus or minus 25 or so. 4 more people walk in the door. Is there 304 people in here now? Like, we don't know. There's probably still about 300 people in the room. So you could think there's a lot of people are going to have to come in the room to bump me up to a higher number on my approximation. So you could think if I'm doing a problem where I have 300 plus 4, that this could still end up being 300. Now, it all has to do with the way we look at numbers, the way we treat them. If we're treating this as a measurement, if I'm treating this measurement here as just being 1 sig fig, or maybe 2 sig figs, and let's think about the difference a little bit. Can you see the difference between 300 having 1 sig fig versus 2 sig figs versus 3 sig figs versus 4 or 5? The difference is whether you're thinking it's like 300 plus or minus about 100, that's what we mean by 1 sig fig. If we mean 2 sig figs, then it's going to be about 300 plus or minus about 10 or so. It could be a little bit greater, but thinking that there's some uncertainty in that second digit in the number. If we then had certainty in the last placeholder in the number, that'd be plus or minus 1. And we could keep going. You could have 300 for 4 sig figs. That would be 300.0. That'd be about plus or minus 0.1. And we could keep going. We'll stop here. But you can imagine we can keep adding zeros, and we're just adding to the precision. And let's just wrap this up for the counted. That's 300 exactly. Like when we count 300 students, if we counted 300 students in this room, that's an exact quantity. When we start thinking of, well, how many digits are significant in that quantity, like there's like 300.0 out to infinity digits that are significant. So this would be an infinite number of sig figs. Which may be hard to imagine, but it's just a perfect number. It's just this is the numbers we think for mathematics. So we see a number, and you're not thinking it's a measured quantity, it's just an ordinary number. It's just like a perfect number of sig figs. Like when you start thinking like 100 centimeters to a meter, there's exactly 100 centimeters in a meter. Like we're not like saying, well, there's roughly 100 centimeters in a meter. There's exactly 100. So when we start thinking rules of sig figs, we have to start thinking, well, the rules apply to the numbers that are inexact. The rules are going to apply to the values that are underlying in our problems. They're going to be the numbers that come from measured quantities, or the numbers that we're imagining are coming from measurements taken in, say, a laboratory. So let's think of a couple different type of numbers here and try to think of how many sig figs they contain. So again, 12 counted eggs. I hope that we can see that as not two sig figs. I'm looking at this number here. I can see 2 digits, but if I count there's 12 eggs, I know exactly I have 12 eggs. And so this would be an infinite number of sig figs. It'd be like 12.0000 out to infinity, okay? So when we count things, we can be perfect with our sig figs. We don't have to worry about rounding off something based on a number that's perfect. So if I say you have 12 eggs, and then you're going to have 12 dozen eggs, you perfectly have 144 exact eggs, right? Like there's no like inherent uncertainty in that. There's no like, well, like maybe we should round it to 140. No, if you have 12 dozen eggs, you exactly have 144 eggs. You know that for a fact. You don't have to worry about where to round that number off to. But now I tell you, you have an object you measured with a volume of 12 inches, let's say, and then the other side we measure is 12 inches, and this becomes a different problem. So if I say you take a 12-inch by 12-inch measurement and you multiply that together, now the rules of sig figs are going to come into play. We need to see what the rule is for multiplying, but now, like, when I see this measurement here, this is a measurement. And when I read 12, I'm going to read that with 2 sig figs. And the whole thing here is, like, I can't really count the measurement. When I'm looking at a measurement, I'm using a ruler or a device or some sort of way to measure the volume, or excuse me, to measure that length. And When I use that tool, the number of digits I write down are telling me how precise that measurement can be made. So I'm looking at this number here and saying this has 2 sig figs. And the other value has 2 sig figs. Again, we're gonna see the rule for multiplication in a minute, so maybe we won't know where to round this to, but when I get 144 here, square inches, I'm going to actually end up rounding it to the second sig fig. We'll see why in a minute, but I'm going to end up rounding that to 140 square inches. Okay? Now, I just want us to fundamentally see the difference between that is because 12 was some measured quantity. There's some inherent uncertainty here. When I see 12 inches, I'm thinking it's plus or minus 1. That there's some inherent inexactness or impreciseness in that last digit. And that uncertainty is why I'm going to end up rounding that value off later. We'll take a look at the rules in a minute. So for here, let's just try to count how many digits are significant in the number 105.0 liters. So our next example here, 105.0 liters. So when I look at a number, I start to count how many numbers are there in the value that are significant. And so 1, 2, 3, 4. You can think of it this way, that this is the most significant number. This is the next most. The 5 is the third most significant digit. Like we're really certain there's at least 1,000 liters. We're really certain there's 1,000 that second sig fig. We're really certain that there's 105 liters. Then we have some inherent uncertainty in that last digit. That's our uncertain digit, but it's still significant. So this number here would have 4 significant figures. So when I look at a number, like all the numbers from the left side, so if I have a decimal point, the numbers on this side of the decimal are significant, the numbers on this side are significant, everything in between is significant. Now, when I see 0.0305, how do I treat the zeros that lead out here? Well, those are what we call placeholders. They're just like holding the place for where our number begins, so they're not significant. So those first, like sometimes we call those leading zeros. The leading zeros aren't significant, and the first actual number, the first like integer we see there, 3, that's where we start our counting of our sig figs. So here we have 3 sig figs. So we have the 305 as our 3 significant digits. So only 3 sig figs and 0.00305. So when you see the 0 starting a number, those don't count. They're just holding the place. You can think about going to scientific notation. If we go to 3.05 times 10 to the minus 2, that you should have the same number of sig figs. And so going to scientific notation, 3 sig figs, so that matches up. So we're good there. Now, when I look at a conversion factor should either be defined or exact or very, very precise. We wouldn't want to lead to a lot of rounding based on some conversion factor that we should probably be able to look up very precisely if we need to. There's other conversion factors like this one here, 1 inch to centimeters. The inch to centimeter conversions, 1 inch is 2.54 centimeters. That's an exact definition. There's exactly 2.54 centimeters in an inch. When I look at this conversion factor here, this has an infinite number of sig figs. When we start thinking of our sig fig rules, we're not going to be rounding off because of using this conversion here. I don't look at this and say that's 3 sig figs for 2.54. I don't look at the 1 inch and say it's 1. This is a perfect, this is an exact conversion. Imagine you take a volume reading over here. This is kind of getting at the idea of interpolating between scales. We see 85 to 86, so we're at 85 here, 85.5, 85.678, and then we're somewhere between what would appear to be 85.7 to 85.8 milliliters. Or I'm sorry, 0.6, 0.7, 0.8, no, 85.8 and 85.9 milliliters. And so you can see that we don't have to call it 85.8 or we don't have to round it to 85.9. We can actually interpolate. What do you guys think is the best interpolation there between our scale? What would you go with? 85.8, probably 5? And if you're sitting there saying, well, I would have went with 85.6, if you're saying I would have went with 85.4, then you kind of get the idea here that there's some uncertainty in that digit here. So there's a little bit of uncertainty here, but we're more certain that it's probably 5 or 6 than it is 1 or 9 than other numbers. So there's some significance in those numbers. So we still count all of these digits here as being significant. So I get 3 sig figs off this measurement here. So the last digit, even if you're using an electronic device, it's always making some interpolation for that last placeholder that it's showing you. So every time you use a digital reading, the last digit you see on your screen is the uncertain digit where there's some inherent impreciseness. And then if you use an actual scale like this, you can usually see it with your eyes and interpolate between. Yes?
It's graduated cylinder would be 85.85 and 85.5 is 46.
Oh, yeah, yes, you are very correct. Thank you. It is 85.85. Yes, I determined this to be about 5 and I lost the 8. So yeah, 4 sig figs. Good job. Thank you. So yeah, the key is you don't have to round, you can interpolate, and when you interpolate, you can get the idea of some inherent preciseness. Now you could say, well, why don't we just round that to 85.9? I mean, you can. It just then has one less significant figure, and then it's going to lead you to round your result off later to have one less digit in it once we see our formal rules for sig figs. Now let's deal with one other number real quick. What if I just say 150 grams? Like, you see 150 grams written. How many sig figs should we imply this is, or read this when we see this number here? This 0 here is actually really hard to interpret because we don't know if the device we were using could have read 151 versus 152 versus 153 and it just happened to read 150, or if that was some scale where it was, 100, 200, and it was like right in between, so we went with 150. So we have a hard time interpreting the 0 here where there's not a decimal point. If I see a number like this, it's actually really easy. So if I see this number here, there must be a reason to write that point 0. Like that would not have been written if it wasn't significant. And so then that makes all 4 of these digits significant. So I get 4 sig figs for 150.0, really easy when I see a point 0. Because I don't have a decimal point here, I'm only going to interpret the first 2 digits as being significant, so I'm going to assume 150 grams is only 2 sig figs. Now, if I'm told more information, then maybe I could determine the third digit significant, but I would have to have more information. Now, occasionally, you might see this written. This is one way. If you actually physically see the decimal point written, then you would be like, well, there must be a reason they wrote the decimal. There must be them trying to say all 3 digits are significant. I don't use this notation too often, but sometimes you might see it. Maybe, I don't know where you would see this. Maybe something to do with the lab, perhaps. But this is like some ways that you may have seen before. How do we note 3 sig figs here? We'll just put a decimal point in. Well, another way we can write, and the really way to be definitive, is to use scientific notation. So if you go to scientific notation, we can write 1.5 times 10 to the 2. And this is a very easy way to show 2 sig figs, right? Because there's only 2 digits there. And for me to show 150 to 3 sig figs, I would just simply write the 0. So decimal points are helpful. If we have a decimal point involved somewhere and there's a 0 after it, then we know it's significant. If I don't have the decimal point, and I see 150 without a decimal point, I don't know if that 0 is significant, and I'm assuming it's not. So I just see 150 grams, I'm assuming that's 2 sig figs. If I see a decimal point, perhaps, I would say, well, that probably means all 3 are significant, but a better way is to go to scientific notation so we can be really unambiguous to show how many digits there are significant. Okay, so let's get into our first type of calculation. The first type will be addition and subtraction. So when we're doing calculations, it's going to be the measurement that we're more imprecise with. It's going to be the measurement that has probably the least either digits in it or the least number of sig figs. It's going to lead us to round off our results. So here's our big rule here for adding and subtracting. So when adding and subtracting, we're going to report results to the same placeholder as the value with the greatest value or the greatest quantity placeholder. So when we look at addition and subtraction, I don't actually necessarily count 2 sig figs plus 2 sig figs. I'm not really counting sig figs. When we get to multiplication division, you're going to see that we are. And for some reason, this gets really confusing coming back to addition and subtraction once we see the next rule, is that everybody wants to count sig figs and say 2 sig figs plus 2, we should round it to 2. No, that's not the rule. The rule is all about placeholders. It's about, I have a ones placeholder, I have a ones placeholder, I add these 2 numbers up, I get 150 grams. But I get 150 grams or that 0 is significant. So my number is going to be significant to all 3 digits. So I'm going to end up with 3 sig figs here And I should write that, if I want to be clear, 1.50 times 10 to the 2 grams. And let's think about why this works and why we would round off this way. The inherent uncertainty here is plus or minus 1 gram. That's what we mean by the 75. We have some uncertainty in that 5 digit to about at least a value of 1 in that digit. And so imagine you have 75 plus 75, that's 150. Well, the uncertainty, imagine like if we were off on both numbers, as bad as we could probably be off would be 74 plus 74. And so that would be 148. And if we were high, if we were 76 plus 76, if we were plus 1 in each of those digits, about as off as we could have been in those measurements on the high side, we would have been 152 grams. So you can see the plus minus, the uncertainty is falling in that 1's placeholder. It's falling in that 0 digit in the number 150, meaning it's a significant digit. So you might look at it and say, and this is where like a stats class, who has seen stats and have worked with the uncertainty? Somebody probably has in this room. Probably a lot of you guys, I see some hands. And so in a stats class, you learn how to actually take the plus minuses and propagate them through the math. And if you learn to do that, you'll see the uncertainty is about 2. It's going to be about plus or minus 2. We can kind of almost see it playing out just looking at the numbers here. So the uncertainty is going to work out to be about plus or minus 2. The uncertainty is in that 1's placeholder. So the rules of sig figs are really trying to save us from doing some more advanced mathematics and some statistical analysis on our work here. Now we do subtraction, same thing. If I have hundredths place minus hundredths place, the result should be rounded to the hundredths place. And so I'm going to throw this into a calculator just to make sure I don't mess up the arithmetic. I get 20.01 units grams. And I like to show when I do sig fig problems that we see values that are inherently something that was probably measured, because we see a unit like mass, like length, a lot in these examples that I like to use, so that we're not changing or thinking about mathematics as much as we are the mathematics involving measurements or inexact quantities. But anyways, I get 20.01. All 4 of those digits are significant. And it's important that we necessarily don't just look at the number here and say, how many sig figs would this have if we saw this number? Like if you go back to the previous 150, I don't want us to get to a point where we're just looking at our calculator screen. If it says 150, I'm not interpreting 150 how many sig figs. You remember on the previous page, I said that should be interpreted as 2 sig figs. We see based on the sig fig rule, we get 3 sig figs. So we have to interpret how many digits are significant by the rule. So we apply the rule, we saw 150 has 3, I apply my rule, I see I get 4 sig figs here because my value should end in the hundredths place. Now let's see where we have a mismatch between the 2 numbers. So if I have hundredths place plus the 10,000ths place, so let's imagine we use 2 different types of balances. So a top loading balance gives you 2 decimal places. You'll use these in the lab. We have the analytical balance that goes out to 4 placeholders or 4 decimal places after the decimal point. So if we have hundredths place plus 10,000ths place, let's do the math real quick. So we go 125.05 plus 4.4140. So my calculator says 129.464. And so I need to round to that 6th digit. I need to round to the hundredths placeholder because I have hundredths plus 10,000ths. It's like we lose that part of the precision. It's like the extra 2 digits we got on that second measurement were unnecessary because we just are going to lose them in the rounding anyways. And so, but it leads me to kind of stress and think when we see numbers like 25.05 and the 4.1440, that those just come from 2 different tools. Like when we see different precision for different numbers, we see different numbers of decimal places that our results are ending in. It's just implying that we use 2 different types of balances or tools to come up with those numbers. So I go 129.46, apply an ordinary rule of rounding. If it's 5 or greater, round up. If it's less than 5, round down. And so 129.46 grams to 5 sig figs. So note that never were we counting sig figs. I was never looking at it being 2 sig figs plus 2, how many should it be? Or it's 5 sig figs plus minus 5 sig figs. We're not counting sig figs here. We're looking at our placeholders. Okay, so then when we get to multiplying and dividing, multiplying and dividing, this is actually a very easy rule. It's just the hard part is not applying it to addition and subtraction, just applying this to multiplication and division. So the multiplication division rule is the results are reported with the same sig figs as the value in the problem that has the least number of sig figs. Okay, and so we're counting sig figs here, and it's the one that has the lesser, of course, it's going to lead to our rounding. And so when I do 75 times 75 meters, this kind of comes back to the 12 times 12, like inches going to 140, if you recall. We count our sig figs here. And so when I get 5625 square meters, just as the simple result on the calculator screen, I need to round this to two significant figures. I need to round this to 5,600 square meters. Okay, and the reason I do so is to apply the rule. So if I have two sig figs times two sig figs, I need to end up in a result here where I get two sig figs. And so to round off to two sig figs, here's my first, there's my second. So I, of course, round off to the two most significant digits, so 5,600 square meters. So that would be the best result for the problem of 75 meters times 75 meters. Now, again, I'm not saying 75 times 75 should be 5,600, only in the case where it's precisely 75 plus or minus 1 meter plus 75 plus or minus 1 meter. It's the inherent uncertainty in that one's placeholder. Now, imagine you go 74 times 74, 76 times 76. Let's do 74 times 74 real quick, just to imagine we're low on both of the measurements. That's going to be 5476. And if we're 76 times 76, if we're off, but on the positive side, then that goes to 5776. So do you see how our uncertainty is going in that hundreds placeholder? Like our up and down is falling in that hundreds placeholder. Again, if you go to a stats class and you take the plus or minus 1 in 75, you're going to see that the plus minus on the result here of this arithmetic would be about plus or minus 100. So the uncertainty is falling in that hundreds placeholder. So again, we don't want to do the stats. We don't want to do the arithmetic that's involved there. We don't want to teach that to you yet. Other classes can teach that to you. We just want to know a simple rule. Count two sig figs times 2, you round off to two sig figs. So I see, like let's say the object I determine one of the sides is 75.00. So I get a nice device, a better ruler, determine one side 75.00, but I don't do it to the other side. I just wasted my time, right? Because 75.00 times 75 also has to go to 5,600 square meters to two sig figs. So 2 times 4 sig figs, I round that to 2 sig figs. So I would have to determine both sides to 75.00, both sides to 4 significant figures, both ending in 0. And then I can round that result to 5625 with 4 sig figs. So I'd have to go 75.00 times 75.00 if I wanted to know for sure that that object had a area of 5625 square meters, but my certainty is only still plus or minus 1, right? So I'm still not certain it's exactly this. It's still plus or minus 1, 4 sig figs. And so you can think here, a lot of times when we think 75 times 75, why isn't it exactly 5625? Well, like when you're dealing with measured quantities, nothing's ever exact, okay? And so the question is, well, how precise can we be? 75.00 times 75.00, then we can be precise to 4 significant figures. Add another 0 to both numbers, you can go to another placeholder, you can add a 0.0 to it. So you can keep going with the numbers if you wish. Division works the same way. 2 sig figs divided by 3 sig figs. This result here should be rounded to 2 sig figs. And so to do the math, 7.5 divided by 4.55, that gives me 1.648. Let me just go this way on our screen, just so I can see that I'm going to round this to 1.6 gram per milliliter to go to 2 significant figures. And so again, multiplication division, pretty easy because I'm just counting sig figs, and counting sig figs is easy, right? Because we can just look, 2 times 4 sig figs goes to 2, 2 sig figs divided by 3 sig figs goes to 2 as well. So the counting of the sig figs, pretty easy to do, pretty straightforward here for multiplying and dividing. But the key is, try not to apply this rule when adding and subtracting. So when we go back to our addition problem, if I think again, if I'm doing, 25 plus, 4.5, that I'm ending this digit here and that placeholder. So I'm not counting sig figs as much as I am just seeing where the digits happen to fall. So this value here would go to 29.5, and I'm going to round that to 30. And let's throw some units here just so that we're clear that these are measured values. So I'm going to round this to 30 grams, but to 2 sig figs. So 3.0 times 10 to the 1, 30 with a decimal point, noting 2 sig figs. Now, of course, most of the time, we don't do just addition or just multiplication, we do mixed math operations. So what do we do when we have a problem that involves multiple math steps where we have some maybe addition or subtraction going on, and then also some division or multiplication going on? The key is we have to track the number of appropriate digits through a multi-step problem, generally rounding off just at the end. So what that would mean is when I look at a step here, if I have to round before I do the division, I'm probably going to hold off on rounding until the very end. I'm just going to like sort of note where the sig figs fall. We'll see some examples of what that really means if that part's confusing. But try to round at the very end of the problem. This is more of an issue with lab. So in lab, you're going to do a lot of calculations. We're going to go from A to B to C to D to E. You're going to go through a bunch of different math steps. And if you round with every step and then look at your final result versus keep an extra digit each step of the way, and then just round off at the very end, but where you're still noting, okay, step A should have 3 sig figs, but I kept the 4th just to keep it there in the calculation. Step 2 should have 3 sig figs, but again, I kept a 4th. If you just keep an extra digit or two, but kind of note where the sig fig falls, that will be really helpful for lab. Most of your exam problems you ever see, this will be inconsequential. So on an exam or homework problem, it might be helpful to think about it, how there's a little bit of a difference between the two results, but practically speaking, I don't think you're gonna miss any question due to this sort of rounding situation. This problem here, 7.5 plus 2.6, do you see how, because I do that step first, I have to, by order of math operations, I have to do that addition before I can do the division. So I come up with 10.1 grams when I do that addition, because I have tens place plus tens place. Let me do this over here just to make sure that we're seeing that I want to round the result to the higher, to the tens place, because both values are to the tens place. So I get 0.1. So I get 10.1, all 3 digits being significant. So 10.1 has 3 sig figs that we see here from analyzing the addition step first. So I do the addition step first, I apply the addition rule there, then I do the division, then I apply the division rule. And so 3 sig figs divided by 3 sig figs should result in how many sig figs? 3. So we keep 3 sig figs here, so 10.1 divide by 4.55, I got 2.22 grams per milliliter. So I need to go to 2 sig figs. Or, I keep messing numbers up in my head. It's clearly 3 sig figs. So we go to 3 sig figs here. Okay, now let's think about something real quick. We saw division in this step. You may look at this problem and said, okay, I see we're dividing and I see 2 sig figs. Why is it not 2 sig figs? Well, the key is that we're not dividing the 2 sig figs by the 3 until we've added the number with another value that has 2 sig figs, and we end up with that 3rd significant digit. I haven't thought of it this way, but if you imagine separating the 2 steps of your calculation, if you imagine separating off the 7.5 divided by 4.55. I'm sure somebody's thinking, well, what if you did 7.5 divided by 4.55, and then you add 2.5 plus 4.55? I don't want to go through the arithmetic, but I bet you end up with something that has tens place plus tens place, and you keep all of the digits again. So just think, by order of math operations, where do I do my rounding? So I add first, apply the addition rule, then I divide, apply the division rule. So just apply the rules in the sequential order that we have to do the calculations. And we'll see quite a few examples of this, and we'll see examples where we have to add zeros to a number so we can make sure we properly state just how precise we can know a number. And then we'll see most of the time we're rounding off, where we have like 10 digits on our calculator screen. We're going to figure out if we're rounding that to 2, 3, 4, however many sig figs. So let me throw this problem to you guys just for a minute here. So we have, a problem here. Let me just give you guys a minute or two to try to work out how many sig figs this result should have. Feel free to talk with your neighbors if you wish. Still see a few of you guys thinking. I don't know if I'm going to go too fast by asking the question. Does anybody think it's A? Probably not. Anybody think it's B? C? How about D? Does anybody oddly think it's E? Yeah, E doesn't make much sense. So the first thing I want to talk about is just do the calculation. Just do 300 times 400, divide by the quantity, 2.5 plus 7.5. Like, definitely do the calculation and see what you see on your screen. But then let's not fall into this trap. So one of the traps is you look at the number and you say, well, my calculator says 1,200. Earlier you said 1,200 should be interpreted as 2 sig figs. That's not how we're going to think about this problem. So I don't want to just look here and say 1,200 is that, how many sig figs is that? That's a different context. If I told you a different problem, if I said you have 1,200 grams of something, yeah, 2 sig figs. I see 1,200 on my screen, I have to go through the thought process of applying the sig fig rules. So different context of seeing 1,200 saying 2 sig figs versus looking at this number here, I have to interpret the rules to determine the number of sig figs here. Now, I can do the multiplication step on top perhaps first. How many sig figs would 300 times 40 have? This would have 4 because I have 4 sig figs times 4 sig figs. So this ends up being 4 sig figs here. And then my denominator, 2.50 plus 7.50, ends up being 10, but 10.00 because hundredths place plus hundredths place should be rounded to hundredths place. And so I get 4 sig figs in my denominator as well. And so again, just to make sure we're seeing this, 2.50, 7.50, we add these up, they're both good to this placeholder here. So I get all 4 digits being significant in 10.00. So that has 4 sig figs. Then I go 4 sig figs divide by 4 sig figs, I should keep all 4 of those digits as being significant. So I'm significant out to this placeholder here. That would be 4 significant figures. And so 1,200 with 2 sig figs is inherently a different number. It's less precise than 1,200 with 3 sig figs. That's less precise than 1,200 with 4 sig figs. We could have seen 5 or 6 or 7 if we had even more zeros in our numbers here.
Why don't we add the additional 0 to 10 to 10.00? Would we do that to show that that third figure is significant?
Well, for 10.00, I'd say 4 digits are significant. So I go 1, 2, 3, 4. And so because of just where the zeros were falling in the 2.50 and the 7.50. So we're good to the hundredths place. And so 10's good to the hundredths place, which just happens to give it 4 sig figs. Okay, and so then for our division step, we're just simply counting 4 divided by 4. We keep all 4 digits. Yes?
So if you measure out like 1,200, would that be 2 sig figs since you calculated it as 4?
Yeah, so the question being, so like if you imagine you put something onto a balance that for some reason only gives you to the nearest 100, it reads 1,200, then yeah, that's 2 sig figs. And so This would be like, those old balances you would have the weights that you would counterbalance. You probably use these. I'm sure you guys still use those in science at some point. Did you guys use balances like that? I mean, I did. And so maybe you only had masses to the nearest 100. So you were measuring maybe really heavy things. So you come up with 1,200 grams. So 2 sig figs, that's a different process or inherent idea here of coming up with 1,200 with 4 sig figs. Now, just to unambiguously show this, I would probably write it this way. That 1.200 times 10 to the 3 meters per second would unequivocally or unambiguously show all 4 of those digits being significant. So this here, using scientific notation, is a way sometimes to show how many of those zeros are significant in our result without being unclear. We could throw the decimal point in. If I'm like doing work on a lab or something, I'm just like underlining the last digit that's significant. So I underline a lot when I'm doing problems. So if I need to do another step, I just kind of made note with the underline. Now I used the word accuracy versus precision earlier. Like I was just saying it with 1,200 with 2 sig figs versus 3 versus 4. The difference is the inherent preciseness. So how well we can characterize a number is related to its precision. Like you look at the speed of light's a good example of this. You say the speed of light's 3 times 10 to the 8 meters per second. I say, well, that is the speed of light to 1 significant figure. It's the speed of light, if you go 3.00 to 3 significant figures, that would be correct. But to 4, it's 2.998. To 5, it's 2.9979. I don't have them memorized past that. So you can obviously know certain values have been characterized to a really high degree of what we would call precision. And so then when you say, is that really the speed of light, then that has to do with the accuracy. So there's an inherent difference between precision, which is how well do we characterize a number or how well are we hitting our target or a target. So we can look here and see that all 3 of those darts are in the same location. That's what we call a really precise throwing of the darts. Now, was that the target? Now, let's say the person throwing those darts was aiming at the bullseye. Then you can say, well, that was really inaccurate, but it was really precise. And so precision is how closely individual measurements agree. So we do a measurement, we get this number, we do it again, we get that number, we keep getting the same number. That's precision. Is that number the actual true value? Is it really what we were supposed to be getting? That's accuracy. Accuracy is how close we are to the target. And so if we have 3 measurements that are all over the place that then average out to a bullseye, then that would be imprecise, but averaging out to being pretty good. So you can imagine doing an experiment where you get 3 answers that are each individually wrong, but the average is a good number. It's actually the intended target. Now that would be imprecise work, but then overall maybe being accurate on the averaging. But if you want to be precise and accurate, you got to hit the bullseye every time. You want to get an experiment that has a small uncertainty, and then the averaging out of those experiments and trials gives you the intended result. So precision's repeatability. Precision's also what I think of as how many digits. So 2 versus 3 versus 4 digits, that's relating to the precision. How close that number is to whatever it's supposed to be representing, that's relating to the accuracy. So accuracy is how close we are to the target. So experimentally, when we think about how this type of picture applies in the lab, it's like every time we do an experiment, how accurate was the work? How close was it to the actual value? This is why a lot of times in a lab, you compare your final result to some trusted value to see how accurate the work was. And then you might do 2 or 3 trials to see how well your trials compared, how precise you were with your work. We'll do a couple. I just want to scroll through just both for me to see and for you guys to see. We only have a couple slides left. We'll do a density problem. We'll really define dimensional analysis, even though we've used it a few times. And we'll do a couple conversion problems, really just this one problem here to wrap up chapter 1. Then we'll be into chapter 2 on Wednesday after those couple slides, wrapping up chapter 1. All right, guys, that'll do it for today. Have a great rest of your day.